Hello everybody. In this last lecture of module 8, we will still continue with the design of root or design using root locus methods. Now by looking at improving both the transient and the steady state behavior, which means we have to design both the lead and the lag compensators. Okay, so how do we go about doing it? So far what we have learned is that the lead compensator is suitable where or in scenarios where the transient response is unsatisfactory, right? And we saw that this is essentially that you are adding a 0 which will pull the root locus to the left, and then you add a compensating pole so that you could realize it physically, right. So once the transient response is satisfactory, or in problems or in specifications where we don't have to worry much about the transient response, and we have to improve the steady state response, or improve the steady state errors, we use a lag compensator, right. And in this, and while we do these two design procedures, so while designing the lead compensator, we would like the effect on the steady state to be minimal or maybe sometimes improve, whereas when we design the lag compensator, we would want to design it in such a way that the system transients are not affected, and therefore we look at keeping the angle to less than 5 degrees. And we also saw the effect of adding a lag compensator is that it just shifts the root locus slightly to the right. Okay, in case of specifications where neither the transients specifications are met nor the steady state is satisfactory, we would go for designing both lead and lag compensators. Okay, so how would it look like? Well, so if I look at the construction, well, you have a general gain of the compensator, we will have a lead component, a lag component here in such a way that alpha is less than 1. This ensures that the pole is further to the left of the 0. Beta greater than 1 ensures that the pole is to the right of the 0. So in a standard procedure is whenever we have to design a lead and the lag together, we first design the lead compensator and then a lag compensator. So first we try to meet the transient specifications and then go to the steady state compensation. So if I just look at, okay, what do I need to know here? Well, the unknowns are tau 1, tau 2, alpha, beta, and of course, G can be computed directly from the root locus once the specifications are met. Okay, so if I were to look at how does the realization of a lead lag compensator look. So first case 1, where if you look at here, so alpha is less than 1, beta greater than 1, so I can always choose a combination such that alpha times beta is 1. So this will ensure that alpha is less than 1 and beta is greater than 1. So this circuit here, it realizes a lead lag compensator just with passive elements, right. So you know all these guys here are passive elements. However, you have little less freedom, right, because once you choose the alpha here, the beta here is fixed, or vice versa. So once you fix a beta, you don't have too much control over the alpha. So first we design a lead compensator which fixes parameters tau 1 and alpha. So with alpha fixed, I can prove, or what we even saw earlier was that the lag compensator, that this guy can improve the steady state error by a factor of 1 over alpha. Now if this alpha, which comes as a result of designing the lead compensator, is not or does not provide the satisfactory steady state response, then I would go for the design separately. Okay. Okay, in the next case where I would want to choose my alpha and beta separately in such a way that alpha times beta is not 1, then okay, so first let us look at how the series, how the cascade of these two compensators looks like. To maintain this transfer function, I would have to ensure that there is no loading at the output of system 1, right. So if you see, if I just remove this amplifier and I just plug this in here, this may not be, or this will not be the overall transfer function, as we saw in one of our very earlier lectures when we were deriving transfer functions, right. So what I put here is amplifier of gain 1 in such a way that the overall transfer function now is just the transfer function of this multiplied by transfer function of the lag compensator here, right. So this Amplifier acts as a buffer between the lead and the lag and helps in designing the lead and the lag separately. So here I can choose tau 1 and alpha independently of tau 2 and beta, right, and I still have to satisfy this one, that alpha should always be less than 1 and beta should always be greater than 1. Okay, so we'll start with a problem directly, right. So now we know the theory of what are the steps involved when I want to design a lead compensator, and what are the steps involved when I want to derive a lag compensator. So let's say I am given a plant which looks like this. G of s is 10 over s, s plus 1.2, s plus 6, and the desired specifications are the damping coefficient being 0.5 and omega n being 2, and this corresponds to a peak overshoot of 16.3%. So I know the formulas to compute this, and a settling time of 4 seconds. In addition, I also want or I desire that the error constant should be 50. Okay, so based on these two specifications, I can compute what are the desired closed loop poles, or where should be the dominant closed loop poles, right. That is SD is minus zeta omega n plus minus j omega n square root 1 minus zeta square, and that turns out to be these two numbers, right. So somewhere here and here. So as a first test to see what is an appropriate compensator, I just plot the root locus of this guy and just see if for any gain k, if for I will check if there is any gain k such that the SD lies on the root locus, right. So if I just move along these lines, well, I would see that the SD does not lie on the root locus, right, and therefore just a mere gain adjustment would not suffice. Okay. So the root locus does not pass through the desired closed loop when I am just considering a proportional controller, or I am just adjusting the gain. Okay, so what we conclude from the previous slide by just using a proportional controller is neither the transient specifications are met nor are the steady state specifications. So we need to go for designing both a lead and a lag compensator. So let's start with a simple case when alpha times beta is 1. So the first I would do is to design a lead compensator. So what are the steps, right? So if my root locus of the closed loop has to pass through these desired poles, then the angle contribution at that point, which I call SD of the plant, and the compensator should be minus 180. Okay. So now I know how to compute this G of SD, right. So it's a straightforward procedure. So what I find from all these computations is the angle that the compensator should contribute is 42.5. It's very straightforward computations as we did when we were just designing a lead compensator. Okay. Now the second thing is, while we are designing, is now I know that my compensator should provide an angle of 42.5. Now we saw last time that there are several of these pole 0 pairs that could achieve this one, and what we saw is the best one is the one which is computed by this one, right. So if you remember from the diagram what was gamma, right. So once I know the gamma, I can compute the locations of my poles and zeros, exactly the same procedure, right. You just have to just write down the formulas on the left hand side and then start filling the table on the right hand side. So the method to choose or to find the poles and zeros was something like this, right. And this gives me a compensator which is essentially a lead compensator with 0 at minus 1.2 and a pole at minus 3.15, and all these conditions are satisfied that the pole should be to the left of 0. And the gain at which this occurs on the root locus is at k is 2.915, and this gain also includes this factor here, right. So 10k is what we call as k prime, right, and therefore the gain is k prime over 10, and that is 2.915. Okay, now what is the impact of this on the steady state error? Well, if I look at substituting alpha as 1 over beta and computing the steady state error, I get kV is 1.623. Okay, so let's first look at how does the compensated system step response look like. So the black one is 1 when I just look at these two dominant poles, these two, right. And then I want the compensated system, which is essentially the dominant poles plus the compensator, to be as close to the desired as possible. So, this is what is desired, the black one, right, in terms of the dominant pole analysis, and you see it's actually fairly we are close to each other, and this is the maximum or this is the closest we could get, as we saw earlier in the analysis, based on the computation of this gamma. Okay. Then you see that okay, in the compensated system, my MP is at 17%, which is close by to what I desire, and setting time is also like fairly what I wanted, around 4 seconds. Okay. So, now just to do a little bit of analysis on the contribution of these extra poles and why we have this blue line and why do not the blue and the black line match each other, right. So, I have the systems, the poles of the closed loop system at -7, -1 and then -1 with a plus minus square root of 3, right. And then the transfer function of the closed loop system looks like this. So, look at the dominance condition, right. So, this pole is very far from the dominant poles, right, and then there is a 0 close by 1.226, and this is closer to the pole at 1.3. So, if you remember last time that we actually it was desired that there should be a cancellation of as far as possible between the 0 of the closed loop system and one of the poles here, and you see there these are placed fairly close to each other, and therefore this minimizes the effect or the negative effect on the dominance of the remaining two poles, right. Okay. So, what we see in this when we do the partial fraction expansion is, well, there is a pole at -1.3, there is a pole at -7. This we know is much further away from the desired or from the dominant pole. So, this effect is minimal, whereas the effect of this pole is getting multiplied by a very small number on the numerator, and this essentially tells me that this pole 0 combination is almost like facing a cancellation, and then you are just left with this part of the transfer function which essentially deals with the dominant poles. Okay. Okay. So, the design of the lead compensator ensures that the transient response is satisfactory. Okay. Now, let us see what is the effect on this steady state only by this lead compensator. So, if I compute the velocity error constant, it turns out to be that it is just 1.623, which is much less than 50. This is just with the lead compensator. Now, let me design a lag compensator with the beta being fixed by alpha as 1 over alpha. In that case, if I compute what is my steady state error constant, the new one, with the lag compensator, it just turns out to be this guy, 4.057, and this actually comes in the design procedure somewhere over here, right. With alpha fixed, the lag compensator can improve the steady state error by a factor 1 over alpha, and that is exactly what is happening here, right, 1 over alpha. But this is still not good enough for me, because what I want is kV to go to 50. Therefore, we need to design a lag compensator independently of alpha, right, or in other words, we choose the lead lag compensator which looks like this, right. So, you have the lead separately and the lag separately in such a way that alpha and beta are chosen independently, but with still satisfying alpha being less than 1 and beta being greater than 1. So, what is this beta which I want to design? This is the desired, the beta is the ratio of the desired kV, which is 50, and the original kV which I have. So, what is the kV which I have now is whatever is left after I design the lead compensator. So, I can now get the beta to be the ratio of 50 over 1.6, and that turns out to be around 30.8. Okay. So, with this design, well, now I have to fix where are the poles and zeros of the lag compensator. So, let us simply choose 1 over tau 2 to be 0.1, and this gives me the location 1 over beta tau 2. Right. And what we also have to make sure is that the angle contribution of this lag compensator is less than 5 degrees, and that is ensured by this one, that the angle contribution at SD, which is the dominant pole locations, is 2.4, which is very satisfactory. Therefore, the effect of lag compensator on the transients is very small. So, my overall lead lag compensator looks like this, right. So, it is the gain, this is the lead component and this is the lag component, and let us just compare it with the help of some plots. So, this is what I really want to track, right, the unit ramp. So, just by designing a lead compensator, I see that, well, the red line, that there is a significant amount of steady state error, and by designing the lead lag compensation, I see, well, that the steady state error actually reduces significantly, right. It is obtained by looking at the blue line. Similarly, what is the effect of designing the lead lag on the root locus? So, first when I do my time domain specifications, well, the lead compensation, the root locus looks something like this, and I see that the root locus actually passes through the desired poles. Now, if I do a lead lag compensation, I see that, well, it is more or less preserved, but just which is not very unexpected that the root locus shifts slightly to the right. Okay, so in this lecture we had seen both a passive and an active circuit realization of a lead lag compensator, where this active element came in terms of this amplifier with a gain 1 over here, right, and we had seen also how to design a lead lag compensation based on the root locus method. So, we end this module here, and so we just did one problem in each case, but more or less the problems will follow the same procedures. There are some special cases which we need to be careful of, but we will post some extra notes based on that, and we could possibly discuss them at a later stage if you have any more difficulties. And as a part of the assignment in this module, we will give you a problem, or at least a set of problems, where you need to start from modeling of the plant, you need to use MATLAB several times to check. You actually would be made to solve a design problem with the help of MATLAB, and we'll give you as many instructions as you require. And I hope it actually goes well when we learn a little more when we actually solve a problem by ourselves. So, that will be about the assignment of this module, and the next module we will look at the frequency domain compensations, where we will see what are the specifications, transient and steady state, in terms of frequency domain parameters like the gain margin or the phase margin, bandwidth and several others. And similarly, as we made use of the root locus in the time domain analysis, we will make use of the Bode plot while designing compensators in the frequency domain. That is coming up in the next lecture. Thank you.